Great. So now we are live, and we wait a minute or two for people to join. They're already coming in. Lots of people. Okay, very good. We wait a minute or two, and then I will introduce Ofer to the audience. Yeah. Sorry, what did I do now? Sorry, I need to stop sharing. Sorry. Okay, you would imagine that 1 year of Zoom and you know how to stop sharing. Yeah. Okay, good afternoon, everyone. Welcome to this edition of the NITheP Colloquium. My name is Francesco Petruccione, and I have the pleasure of introducing to you today's speaker. And today's speaker is Professor Ofer Aharony. And Ofer studied in Tel Aviv and received his PhD back in 1996. And after a postdoc position at Rutgers University, he became a professor at the Weizmann Institute, where he's still based today in the year 2000. Yeah. Ofer has received several awards for his research that I won't list individually, and today he will speak about some of his more recent work, and the title of his talk is Towards a Theory of Quantum Gravity, which we're of course all very much interested in. And Ofer has worked with Robert de Mello Koch, who was kindly the conduit to invite Ofer this afternoon to be with us. And Robert, you see him also at the top of the Zoom window, kindly offered to coordinate the question and answer session at the end or during the talk if there are emergency questions. Yeah. So now it's time to ask Ofer to start his presentation. And sorry, this is my stupid Teams ringing that is always difficult to block. And Ofer will give us a traditional, very traditional theoretical physics lecture. You already see him standing at his blackboard. Yeah. So Ofer, over to you. Thank you very much for offering the talk.
So, okay, thank you very much. It's a pleasure to give this talk by Zoom in South Africa. I hope that next time I'll be able to do it in person. And this will be a Blackboard talk, so I'll try to keep it informal. And please do stop me with questions at any time. I mean, I'll be happy to answer any questions. So I'll start by reviewing very generally the problem of quantum gravity. I won't assume that you know anything about it. In the second part of this talk, I'll review what's called the Ads Cfd Correspondence, which is our main tool to attack this question. And then the third part of the talk will be about my recent work about the derivation of Ads Cfd for vector models. This will be based on this recent paper in collaboration with Shai, Chester, and Erez Urbach, following earlier work by Robert de Mello Koch, together with Jevicki, Suzuki, and Yoon in this paper. So let me start very generally. So the problem of quantum gravity arises by trying to put together or to reconcile the two main revolutions that happened in physics about 100 years ago, which are general relativity and quantum mechanics. So general relativity is basically the statement that gravitational interactions can be described in terms of the metric of spacetime g mu nu of x, such that when we have matter fields, then they cause fluctuations of the metric, and then the metric transfers the gravitational force onto other particles. So that's one of the main features of general relativity, which arises naturally when you try to reconcile gravity with special relativity. And of course, general relativity has been very successful in the last 100 years. It agrees with all experiments done to date in scales ranging from the lab scales to stars, black holes, and cosmology. Now, the other revolution that happened 100 years ago is quantum mechanics, and that, if anything, has been even more successful, of course. It pervades all parts of modern physics these days. In this talk specifically, I'll talk about what happens when we put together quantum mechanics together with a special relativity, and that gives rise to quantum field theory, which is the main framework I'll be discussing today. In quantum field theory, which again arises automatically if you try to join together quantum mechanics with special relativity, the basic objects are some set of fields, phi I, living in space-time, and you can think of them as quantum mechanical degrees of freedom sitting at every point in space, generalizing the electromagnetic field. So you have various fields, phi I of x. And one way to specify some quantum field theory is to say which set of fields you have, and then to write down some local interactions for these fields, which are governed by some coupling constants, which we could call GK in general. Now, if these coupling constants are small, then you can use perturbation theory. In particular, if the coupling constants go to 0, then you'll just have a free field. And of course, a free field theory we know how to solve exactly. But more generally, we can just analyze quantum field theories. Again, if the couplings are small, you can use perturbation theory. If they're large, then there are various other methods to analyze quantum field theory, say by lattice simulations or any other method that you like. Now, in quantum field theory, the main observables are correlation functions of local operators. So you can construct various local operators from these phi's. For instance, you can construct some operator which would be phi I squared of x, for instance. And then the basic observables of the theory are some correlation functions of these local operators. So O1 at some point x1. x1 will now denote the point in space-time up to O(n) of xn. So these are the basic observables in the quantum field theory. And from them you can construct the scattering amplitudes and anything else that you want about the quantum field theory. Now, one important property of quantum field theory is that not every set of possible coupling constants and local interactions gives a consistent quantum field theory. Only some specific sets of coupling constants give what are called renormalizable quantum field theories, if all the coupling constants have non-negative mass dimensions. In those quantum field theories, you can compute all the physical observables in terms of a finite number of parameters so that you can make physical predictions for the physical observables at all length scales. So these are special quantum field theories. Well, if your theory is not renormalizable, then you have to introduce an infinite number of parameters in order to make predictions at all length scales, and then you lose predictivity. So these two fields of general relativity and quantum mechanics have evolved more or less independently from each other in the last 100 years. But it's natural to assume that gravity, and in particular general relativity, should also be a quantum theory, namely that there should be some way to put together general relativity and quantum mechanics. Now, unfortunately, it's very difficult to measure quantum effects in gravity. Of course, we only usually know how to measure gravity at very long length scales, and quantum effects we only know how to measure at very short length scales. So it's very difficult to experimentally test quantum gravity. Indeed, you can estimate just on dimensional grounds that quantum gravity effects should become important at a length scale, which is what's called the Planck scale, which is the only quantity with units of length that you can form from h bar, g Newton, and the speed of light. And this length scale is around 1.6 times 10 to the minus 33 centimeters. So if we could go down experimentally to such short length scales, then we could experimentally see quantum gravity effects. But of course, even in the best accelerators in the world, we're still very far from these length scales. So far we do not have any experimental tests of quantum gravity, but still we believe that these two general principles of quantum mechanics and general relativity should be combined somehow into a theory of quantum gravity. So we can try to construct a quantum gravity theory just theoretically, even without any experimental input, and to see if such a theory makes sense or not. Now, the most naive way to try to construct a quantum gravity theory would be to assume that quantum gravity should be a quantum field theory, like the standard field theories that play a big role in particle physics and condensed matter physics and so on. Namely, to start with this gravitational field and assume that we should try to write down some quantum field theory based on treating this metric as the basic field in our theory, and then quantizing it in the same way that we quantize other field theories. But if we try to do that with an action which is the Einstein-Hilbert action, which reproduces Einstein's equations for general relativity, then we find that the resulting theory is not renormalizable. Newton's constant has dimensions of length squared, so it's not consistent with renormalizability. So trying to construct a quantum field theory to describe quantum gravity just doesn't work. So we must look for some other framework in which to describe quantum gravity. Now, in retrospect, perhaps it's not so surprising that quantum gravity doesn't fit into this general framework of quantum field theory, because, as I mentioned, in quantum field theory, it's important that we have these local operators, and they sort of form the basis for the construction of the theory. While in the theory of gravity, we really don't have any local operators. That's because one of the other principles of general relativity is that we have the theory is invariant under diffeomorphisms of space-time. Namely, it's invariant under changing our coordinates of the space-time from x mu to any other x prime mu of x mu. And this is really a gain symmetry, so that we have to identify configurations that are related by diffeomorphisms of this type. And this means that we cannot, say g mu x itself is definitely not a well-defined local operator, because it's not invariant under these diffeomorphisms. So it's not clear really what are the good, and indeed it's impossible to construct any local operators. So it's not clear what would be the starting point for trying to view general relativity as a standard quantum field theory. The observables that we do have in general relativity are things like scattering amplitudes of graviton. So these scattering amplitudes are well defined, and we can ask what is the scattering amplitude of some number of gravitons to form some other number of gravitons. That is a well-defined observable, but it seems that quantum field theory is not the right tool in which to analyze this problem. So we have to find some other methods in which to discuss the quantization of gravity. So are there any questions so far?
I don't think so, Ofer. Thank you very much.
Very good. So let me make just one more general comment about quantum gravity. So the most successful attempt so far to try to formulate a theory of quantum gravity is what's called a string theory. Now, string theory is very different from quantum field theory. Quantum field theory is based on particles or fields that are really localized at one point in space-time as the basic objects. In string theory, we replace that by strings. They could be closed strings or open strings, and they have some typical length scale, which is called the string scale Ls, and it's related to the tension of the string that fixes its typical size. So in string theory, the basic objects that we can't quantize are not these particles, but are strings. Of course, if we view them from very far away, at distance scales bigger than no string, then they look just like particles. So at long distances, we would get a theory that looks like a theory of particles, but at short distances, it looks very different. So string theory was investigated, I guess, for already 50 years now, more or less. And it turns out that when you try to construct a theory of strings and quantize it, then you can't quantize these strings. And it automatically always turns out that one of the modes of a string is a massless spin 2 particle, namely a graviton, which is naturally identified with the fluctuations of the metric in space-time. So in that sense, string theory automatically gives you a theory of quantum gravity. So it looks like it is a solution to this problem of quantum gravity. Now, we don't know yet if the solution is the correct solution to describe our universe, because string theory has many different possible solutions. And we don't know if any of those solutions actually describes our universe or not, so we don't know if it's the correct solution for quantum gravity in our universe or not. But here in this talk, I'm focusing just on the conceptual question of quantum gravity, so I won't say any more about whether this is the correct solution in our universe or not. But conceptually, at the conceptual level, there's a more serious problem in this solution, which is that string theory, we understand how to describe it. String theory is defined in perturbation theory. We know how to perform computations in the perturbation expansion and the couplings between the different strings. But we don't have any non-perturbative formulation of the theory for a finite value of the string coupling constant. So in that sense, it's not a complete theory so far. Of course, perturbation expansion does not converge like in almost any theory. So the perturbation expansion itself does not define a well-defined theory. So string theory does give us a consistent way to compute, say, graviton scattering amplitudes perturbatively, but it does not provide a full, complete theory of quantum gravity as we would like. So presumably it's a step in the right direction, but it does not yet give us a full complete theory of quantum gravity. So that's the end of my sort of general review of the problem of quantum gravity. Are there any questions up to here?
Thank you, Ofer. I think there are no questions so far. Thank you.
Okay, very good. So this completes the first part of this talk, the general review of quantum gravity. The next development that I want to describe on this long route towards a theory of quantum gravity is what's called the Radius Cfd Correspondence, which was found by Juan Malgocena in 1997. So the way that Malgocena attacked this problem of quantum gravity is to consider a theory of quantum gravity not in a flat Minkowski space, which is the situation that we usually imagine ourselves in, but instead in some different space-time, which is what's called anti-de Sitter space. Now, anti-de Sitter space is a maximally symmetric space of negative curvature. So it's a negatively curved space, which is a solution to Einstein's equations with a negative cosmological constant, so the opposite sign from the positive cosmological constant that we seem to observe in our universe. And if you want to picture what this space looks like, then I'll draw this space for the case of two space and one time direction. So in two space and one time dimension, this anti-de Sitter space looks like a filled cylinder of this type, but where each time slice, so this is the time direction, and each time slice of the cylinder is topologically like a disk, but this disk has the metric of the hyperbolic plane such that the boundary is actually infinitely far away. So one way to write down a metric on this space, we can write down the metric on this space as including the standard Minkowski coordinates dx mu, and then one extra coordinate z, which is called the radial coordinate. And the metric behaves in this way. So in this picture, this coordinate z is the radial coordinate coming in from the boundary of this cylinder towards its interior, such that the boundary sits here at z equals 0. And you see that at z equals 0, any distance in these other x coordinates goes to infinity, such that the different points here on the boundary are actually infinitely far from each other. But the full space is well defined, and you can also check that light rays can go to the boundary and come back in a finite amount of time, so that the space is a causally reasonable space-time. Now, the advantage of considering quantum gravity in this space-time as opposed to Minkowski space-time is that in this space-time, of course, we still don't really have any local observables in the interior because, well, the metric fluctuates in the interior, and we have to divide by all diffeomorphisms of the interior so that we don't have any really well-defined observables there. However, we can have well-defined observables on the boundary, so we can put in some operator here on the boundary at z equals 0 and at any value of these other coordinates x mu. And because of this fact that the metric goes to infinity, or distances go to infinity at the boundary, then the metric at infinity is actually well-defined. It does not fluctuate, and it is legitimate in the theory of gravity in this space to put in, say, sources at points on the boundary, such that in this specific theory of quantum gravity living on this space, some of the observables of the theory include correlation functions of operators that you could insert at the boundary of this space. Say one operator at the point z equals 0 on the boundary, and at x1 in the other spatial coordinates, another one at x2, and so on. So this gives a list of some consistent observables in any theory of quantum gravity in ADS space, namely just the response of this gravitational theory to putting these sources at some specific points on the boundary. And one of the main observations of the Ads Cfd correspondence is that this list of observables looks very similar to the list of observables that we would have in a quantum field theory that lives in one dimension less. So suppose that mu here, say, goes from 0 to d minus 1, so that we have this. So this is the anti-de Sitter space in d plus 1 space-time dimensions. So this looks. The list of observables in this theory looks similar to those of a quantum field theory that lives just in these space-time dimensions and which is parameterized by these positions x along the boundary of space-time. So this So this is at least one indication that there could be some relation between these two very different types of theories, one of them being quantum gravity living on an anti-de Sitter space in d+1 dimensions, and the other one being just a quantum field theory that lives in d space-time dimensions. And the big leap that Maldacena made was to conjecture that perhaps these two theories that look like their lists of observables are similar to each other, could they perhaps actually be completely equivalent? So is it possible that a theory of quantum gravity in anti-de Sitter space is actually completely equivalent to some quantum field theory, and perhaps also the other way around? And this statement of the equivalence between these two very different theories is what's known as the Ads Cfd correspondence. Now, of course, at first sight, such a correspondence between two theories that look completely different from each other sounds completely ridiculous, but we do know in quantum field theory many examples of what are called dualities of this type that relate just in quantum field theory different descriptions of the same quantum field theory. We have, for instance, particle-vortex duality in two space dimensions, or we have Kramers-Vernier duality, exchanging order and disorder operators, and so on. So we have various examples in quantum field theory where we can start with one set of degrees of freedom at weak coupling, and then as we increase the coupling, these degrees of freedom can rearrange themselves into some completely different set of degrees of freedom that would then maybe become weakly coupled when the original coupling becomes strong. And so this gives us dualities between different descriptions of the same theory, and the claim is that the same thing is happening here, namely that a quantum gravity theory living on this d+1 dimensional anti-de Sitter space is completely equivalent to a d-dimensional quantum field theory. And of course, if this is correct, then this gives us a relatively simple way to describe these quantum gravity theories, because we do know very well how to describe quantum field theories, not just in perturbation theory, but also non-perturbatively. And then if they're equivalent to these quantum gravity theories, then of course that would give us a description of these quantum gravity theories, again, for now, not in flat space, which is what we may want to have, but at least in these specific curved spacetimes of anti-de Sitter that are called the anti-de Sitter space. So let me give an example of this, more concrete example of this Ads Cfd correspondence to also illustrate in what ways it's similar or different than the dualities that we have in quantum field theory.
Ofer, we have a few questions.
Yes, please.
Okay, so the first question was asked after you described the fact that string theory is defined perturbatively.
Yes.
And the question is, doesn't quantum field theory suffer from the same problem, i.e. isn't defined non-perturbatively?
Well, maybe for some quantum field theories that may be correct, but for many quantum field theories, we do have also a non-perturbative description of them. For instance, there are many quantum field theories for which we have a lattice formulation. For instance, for QCD, we can just put it on the lattice, and then as we take the continuum limit, we can really produce a description of the theory that makes sense for any finite value of its parameters. So we're not limited to just weak coupling. It's true that it's much easier to do computations in perturbation theory when you have weak coupling, but in quantum field theory, that's not a basic restriction, and there are many theories where we do know how to do computations also at strong coupling, again, either by lattice simulations. In some cases, we can solve theories exactly using integrability or other tools. And in any case, the theories themselves are well defined at all values of the coupling. It's just sometimes difficult to compute at strong coupling, but the theory, we know in principle at least how to compute at strong coupling, and the situation is different in string theory. In string theory, we don't even know in principle how we're supposed to compute beyond perturbation theory. But in quantum field theory, we do know how to do that.
Okay, the second question was asked when you wrote down the metric of ADS, and the question was, what is L?
Yeah, sorry. Oh, yeah, right. Thank you very much. Yeah, I should have said that. So L is the radius of curvature of this ADS space. So I mentioned that the space is negatively curved and it has a constant negative curvature. And L is just the radius of curvature of this space. So that's sort of the typical length scale that you have to go in this space before you start feeling the curvature. So the scalar curvature, for instance, is 1 over L squared. So this is just the radius of curvature.
Okay, the last question that was asked was when you had said that there are no local observables in string theory, in a theory of gravity, and the question that was asked is, in string theory, is the graviton considered to be a localized vibration of the metric, or has the field theory view been completely abandoned?
Yeah, so that's a rather subtle question. I mean, so of course, string theory does have excitations corresponding to gravitons. I mean, so you can construct put the string in the state where it would be like a graviton and so on, and you could have then some wave packet of the graviton and try to scatter it, but the claim is just so say a scattering state of a graviton is a good state in the theory, and you can then compute the scattering amplitudes of these states and so on. What I was saying that just a graviton at some specific point is not really a well-defined object in the theory. G mu of x is not well-defined because it's not invariant under diffeomorphisms. But a scattering state of a graviton, for instance, or a scattering state of two gravitons, that is a well-defined object in string theory and more generally in quantum gravity. And so those are the basic observables. And in some sense, in the case of anti-de Sitter space, to get these scattering amplitudes, we have to take these wave packets to infinity. And the point of the Ads Cfd correspondence is that in anti-de Sitter space, when we try to take these gravitons to infinity, they just go to these points on the boundary. In that case, they localize to a point on the boundary. So that in that case, we do get, instead of these scattering states that form the S matrix in flat space, we get these local observables, and those are then the main observables in quantum gravity on anti-de Sitter space. So yeah, thank you very much for all these questions.
Okay, Ofer, we've dealt with all of the questions. Oh, sorry, one more appeared.
Okay.
If ADS is equivalent to QFT, why should it give more insight into quantum gravity?
Sorry, what? I'm not sure if I understand.
So, if ADS is equivalent to QFT,
Yes.
why should this give us more insight into quantum gravity?
Well, okay, so the question of insight is the question of to what extent can we really understand this in detail, but in the rest of this talk, I'll first ask the question of is it even true that these two things are equivalent to each other? Again, this is a very far-fetched, sounds like a very far-fetched statement that these two theories that have completely different variables and live in completely different spacetimes could possibly be equivalent to each other. If they do turn out to be equivalent, then that means that, first of all, we know how to formulate quantum gravity non-perturbatively just in terms of this quantum field theory. And then in principle, any question that we want to ask about quantum gravity, we should be able to translate into a question of quantum field theory where we should be able to know how to answer it. I mean, at least numerically, if it's a strong coupling, but at least in principle, we would know the answers to all these questions. Again, in practice, it may be difficult, but this mapping, if it's correct, it makes all questions of quantum gravity, again, at least in this context of ADS space, it makes them well-defined. Well, for now, they're not even well-defined. So the main advantage is to make them well-defined, and then we can try to ask specific questions and answer them and so on. So that will be the next step.
Okay, great. We finished with the questions.
Okay. So let me now discuss the first example of the Ads Cfd correspondence. So this is the most famous example that was described in Mello Koch's original paper. I mean, I won't assume any details about this example, so it doesn't really matter precisely what all these things mean. For the people who are not familiar with string theory, it doesn't really matter. So it's on the quantum gravity side, the specific quantum gravity theory in question is some specific string theory called type 2B string theory that lives on a 10-dimensional space, which is a product of a 5-dimensional anti-de Sitter space times a 5-dimensional sphere. And this theory is supposed to be equivalent to some quantum field theory in 4 dimensions. And in this case, the quantum field theory in question is believed to be the maximally supersymmetric, so the theory with extended n equals 4 supersymmetry. So the maximally supersymmetric Yang-Mills theory with this gauge group with this gauge group SUN. So this is a standard field theory that has some non-abelian gauge fields in the adjunct of SUN and has some scalar fields and fermions, and you can write down the Lagrangian for this theory exactly. So this was the conjecture by Mello Koch that these specific theories of quantum gravity and specific quantum field theories are equivalent to each other. And this claimed duality was tested by many computations that were done on both sides, and it was shown that you get the same answer. But so far, there's no derivation that this is indeed an exact equivalence between the two sides. And indeed, because we don't even have a definition of the left-hand side of string theory non-perturbatively, it's not even clear how you would possibly derive this statement, because one of the sides is not even well-defined. But again, it does seem to be a correct correspondence as far as it's been tested so far. Now, what I want to illustrate in this correspondence is how the parameters of the two sides map. So here on the right-hand side, we have basically two parameters for this quantum field theory. We have n, which is implicitly a parameter hiding here inside this SUN gauge group, and we have the Yang-Mills coupling constant, analogous to just E squared in electromagnetism, that parameterizes the interactions of this gauge theory. And in fact, when we do perturbation theory, it's then the perturbation theory actually arranges itself as a power series in GNL squared times n, so it will be more convenient to work in this variable. And then the way that this correspondence maps these parameters, so these are the two parameters that we have on the field theory side, and it's important that we have here two parameters for reasons that I'll explain in a moment. And these two parameters map on the gravity side, so n maps to essentially the length, the ratio between the curvature length of anti-de Sitter space and the Planck scale to the fourth power. So this is, so this governs the strength of the gravitational interactions. I mean, so Newton's constant goes like some negative power of the Planck scale. So this tells us that, this tells us that gravitational interactions are suppressed by powers of, well, 1 over n squared in this case, if you follow exactly the relation between Planck's scale and Newton's constant. So this is one mapping between the two sides. It tells us the strength of the gravitational interactions. And the other parameter, this lambda, maps to the ratio between L and the string scale. So this is a string theory, so it has this typical length scale of a string. And this other parameter, lambda, maps to the ratio between the length scale and the string scale to the fourth power. So what does it mean? So let's draw a two-dimensional plot of the space of these possible theories on the two sides, parameterized by these parameters lambda and m. Now one limit we can take is the limit where this Kaplan constant lambda is small. This is the limit where we can just do perturbation theory on the field theory side for any value of n. So in this regime, the Q of t is weakly coupled, and we know how to do perturbation theory. Well, if lambda is large, then the Q of t is strongly coupled, and we don't know how to do perturbation theory, even though, again, the theory is still well defined, and we can do computations using other methods in some cases. So this is from the Q of t point of view. Now, from the gravity point of view, then what controls the gravitational interactions is actually this parameter n. So if we're in this regime of large n, then in this whole region of large n, gravity is weakly coupled for in this whole range of parameters of large n. And what changes from the gravity point of view as we increase or decrease this parameter lambda is the string scale. Now I should have mentioned this perhaps, but string theories are non-local at the typical length scale of the string. They have this intrinsic non-locality coming from the length scale associated with these strings. So in this case of large lambda, then the radius of curvature of anti-de Sitter space is much bigger than this string scale. So gravity is approximately local. Since it becomes local, distances much bigger than L string, and those distances are still much smaller than the scale of the curvature in this regime here. So this is the regime where gravity behaves like a standard gravitational theory, and is well described by Einstein gravity. While in this other regime of small n, in this regime, gravity is highly non-local, or it's stringy if you want. I mean, because the radius of curvature of spacetime is the same as the typical size of the strings, so the gravity theory is completely delocalized in some sense. However, the theory is still weakly coupled. I mean, so in this regime, even though gravity becomes non-local, the gravitational interactions are still weak. And then the nice thing about this picture, I mentioned before that in field theory, usually when we have a duality of this type, then usually when one side is weakly coupled, the other side is strongly coupled, and vice versa. That's what happens in the examples that I described. But in this example, we have the option that both sides could be weakly coupled at the same time if we sit here in this regime where n is very large and lambda is very small. So in this regime, the quantum field theory is weakly coupled, but also gravity is weakly coupled. The price that we have to pay for this is that gravity is highly non-local. And in this case, it's really a string theory. So it's not really a standard gravitational theory like Einstein gravity, but it is still a classical theory in this limit. The interactions are still small, and we can still understand it classically. So this is a feature that this Ads Cfd correspondence has that is different from quantum field theory dualities, that there is a limit here where both sides are classical. And of course, if we want to try to understand this duality, then in some sense, that's probably the best limit in which to study it. Now, unfortunately, even in this limit, in this case, the duality turns out to be relatively complicated. So even in this limit, it's not really well understood. I mean, here we have a classical string theory, but it's a string theory on a space whose radius of curvature is of the same order as the string scale. So it's a very complicated classical string theory. And also in the field theory, because of this SU engagement invariance for large n, the theory turns out to be rather complicated. So in this case, even in this limit where both sides are classical, we still don't really understand the mapping properly. But in the second example that I'll describe in a moment, we will be able to take advantage of a similar limit in order to understand the mapping explicitly. But are there any questions first about this first example before I move on to the second example?
No questions.
Okay, very good. So this is one sort of typical example of the Radius Cft correspondence, but this example, as I said, even though it does have a limit where both sides are classical, then that limit is still rather complicated. So the example that I'll focus on today is this different example that was constructed by Klobanov and Polyakov in 2002. And in this case, the theories in question, well, the field theory in question is an even simpler theory. So the theory on the quantum field theory side, so we have the quantum field theory side, and we have the quantum gravity side. On the quantum field theory side, in this case, we just have the theory of n free scalar fields. Let's take them to be complex scalars. So we have some complex scalar fields phi of x, and the action, if we use the action formalism to describe these fields, then the action is just the free field action. I'll take them to be, also massless for simplicity. So just n free massless fields. Now this theory, well, by itself is already, so this is with a sum over n, over I, from 1 to n. Now this theory in itself does not have a good Larson limit, which we want to have in order to have this classical description. But this theory has a UN global symmetry that just rotates these n different scalar fields. And if I only look at Uninvariant Observables in this theory, so I just project the list of physical observables onto those that are invariant under this UN symmetry, then that theory does turn out to have a good Larson limit. In particular, for instance, as examples of UN invariant observables, so one type of observables we can construct are things that, again, would be the sum over I of phi I dagger x, and then we can have, say, j derivatives acting on another phi I of x. So this gives us some local operator of spin j, which is invariant under this UN group. And it turns out that in this theory, these types of operators give us conserved spin j currents for any spin j. Usually if we have a field theory that's not free, then it has a spin 2 current, which is the energy momentum tensor, but usually does not have any higher spin currents. I mean, if we want to have non-trivial scattering, then that's not compatible with having any higher spin currents. However, in the free field theory, we do have these conserved high spin currents for any integer spin j. And of course, the existence of these conserved currents means that we have a huge symmetry group in these free field theories, which is what's called high spin symmetry, and which is generated by the charges of all these different currents. So that's the field theory side here. Now, what do we have on the quantum gravity side in this case? So on the quantum gravity side, we should have a theory that has, since it's supposed to be equivalent to this quantum field theory, it's supposed to have the same symmetries. So it's also supposed to have these conserved currents of all spins. And it turns out that to realize them, then you need to have on the quantum gravity side, you must have also massless spin j fields in anti-de Sitter space for every spin. So not just for spin 2, which we usually have as the massless graviton, but in order to match what we have in the quantum field theory, in this case we must have massless fields of any integer spin from 3 and higher. Now in flat space, it's not known, or it's believed to be impossible to write down a consistent interacting theory with massless higher spin particles. However, it turns out that in anti-de Sitter space, so even classically that's believed to be impossible. However, in anti-de Sitter space, Vasiliev has written down a theory of interacting higher spin fields, so just a classical theory of interacting higher spin fields, which does seem to be consistent with this high spin symmetry in anti-de Sitter space. And it's in fact believed to be the unique theory. I mean, such a huge symmetry is believed to restrict the theory, so to determine uniquely the theory without any freedom. So there is this specific Vasiliev high spin gravity theory, again living in anti-de Sitter space in d plus 1 dimensions. And what Klobanov and Polyakov conjectured, basically just by matching the symmetries of the two sides, is that these two theories should be equivalent to each other. So that was the example that they gave. In this example, we only have one parameter. We just have this parameter n. So if you want, this example sits here just sort of on the y-axis here of this plot. We just have this parameter n. And again, the advantage of this example would be that, again here, the 1 over n plays the role of a coupling constant in this quantum gravity theory. And again, in the limit where n is large, both sides are weakly coupled at the same time. So we have a hope of understanding relatively rigorously the mapping between the two sides. and that's what I'll describe in the rest of this talk. So this example, in this limit where both sides are weakly coupled, does turn out to be simpler than the previous example, and I'll describe, and the rest of this talk will be devoted to describing in detail how in this example we construct an explicit mapping between the two sides. So are there any questions before I do that?
Yes, there is a question. Does J have to be an integer, or are fermionic cases also acceptable?
Okay, good question. So here I started with free scalars. So in the case of scalars, I can only construct these, on the field theory side, I can only construct these scalars with integer spin J. So here this J is just 0, 1, 2, and so on up to infinity. But there are similar theories that I can construct. Say if I would have both free scalars and free fermions, then from those I would be able to construct conserved currents also of half-integer spins. And there is in fact a generalization of this duality also to that case. So there is a generalization of Vasilyev's theory that has also these fermionic massless fields of all higher spins, so half-integer spins as well as integer spins. And there is a generalization also to that case. But for simplicity today, I'll just discuss this simplest example, where here we only have scalar fields and the operators all have integer spins. So thank you.
No further questions.
Okay. So yeah, so this will be now the example that, so now so this was all a review of relatively old results, and now I'll move on to describing the relatively new results about how we construct an explicit mapping between the quantum field theory and the gravity theory in this case, and in that way derive this Ads Cfd correspondence. I guess I should have said earlier that, so I now want to derive the Ads Cfd correspondence for this case. Now you should ask in this case, what does it mean to derive a duality when one of the sides of the duality, namely the quantum gravity theory, is not well defined as a quantum theory? I mean, in some cases it's well defined perturbatively, but in this case of the high spin gravity, it's even only known classically. It's not even known in perturbation theory. So how could you possibly derive a duality when one of the sides is not well defined? So what I mean by deriving the correspondence in this case is that what I will show is that we can take the quantum field theory and we can just rewrite the full path integral, say if I use a path integral formalism of this quantum field theory, we can rewrite it so that it becomes quantum, just by a change of variables, it becomes a quantum gravity theory on anti-de Sitter space. And in this way, of course, we explicitly show the equivalence between the quantum field theory that we started from and this quantum gravity theory in anti-de Sitter space. So in that sense, it will be a constructive derivation that will really give us an explicit description of this quantum gravity theory on anti-de Sitter space. So this will be the goal of the rest of this talk. So, and the method that I'll be using to construct this derivation is a method that's called bilocal holography. So, well, I guess I should have mentioned that this Ads Cfd correspondence is often termed holographic because it maps a theory that lives in d+1 spacetime dimensions to a theory that lives in one dimension less, similar to what a hologram does in capturing three-dimensional information in a two-dimensional image. Now, the idea of bilocal holography is that if we look at these free field theories that I described a moment ago, then there is an interesting set of operators invariant under UN that we can construct in these theories, which are bilocal operators labeled by 2 points in spacetime that I can construct by taking the product of the fields phi I dagger at x1 times phi I of x2. So this operator is obviously invariant under the UN global symmetry. And the claim is that in fact this list of operators and their products gives us all the operators that are invariant under the UN group. So this gives all the UN invariant operators, so that it's enough so that any UN invariant operator I can express using this bilocal field instead of going back to the original language of the phis. I can work with this bilocal field. So this formalism was first suggested by Das and Jevicki in 2003, and then it was investigated further in the last 18 years by Robert and many other people. Now, the fact that all the UN invariant operators can be constructed in terms of this bilocal is a highly non-trivial fact. For instance, if I were taking SUN invariants, then there would be additional invariants I could construct, say baryon-like operators with an epsilon symbol and so on. But when I look at invariants under the UN group, then the claim is that this list of observables indeed captures all the possible UN invariant observables that I could write down. Now, in particular, you can see that if I do a Taylor expansion of this as x2 approaches x1, and then I do a Taylor expansion of this, then it reproduces the local observables that I was discussing before, these spin J currents. So, of course, they're all included in this bilocal observable, but the bilocal observable contains much more because it is well-defined for any 2 points in space-time. And again, the claim is that this bilocal observable contains all possible UN invariant observables. And what that means is that what we want to compute on the quantum field theory side, say that if a typical observable on the quantum field theory side, one way to describe it, if I use the path integral formalism, would be to describe it as a path integral over all the fields phi I. With I'll work in Euclidean space for simplicity, so I just have e to the minus this Euclidean action, which is the sum of d mu phi I squared. And then my observable would be some functional of this bilocal field gx1, x2, so I could compute an expectation value, say, of a product of these g's and so on. Those are some UN invariant observables in this quantum field theory. And again, the claim is that these are really all the possible UN invariant observables, so that this is what I want to compute. And now what I'll do in the rest of this talk is I'll show that we can rewrite this same observable. So here it's written manifestly as an observable in a d-dimensional quantum field theory. But the claim is that we can rewrite the same observable as an observable in some quantum gravity theory on anti-de Sitter space. And the way that we'll do that is in 3 steps to rewrite this path integral as a quantum gravity path integral. The first step that I'll do is a change of variables from phi I of x to these bilocal variables, gx1 of x2. So this is just a change of
We
variables.
have a question.
Yes, please.
It's from Shinji. Francesco, can you unmute Shinji?
Yes, I will do so immediately. Here we go.
Hi, Ofer.
Hi, Shinji.
So you can have actually non-singlets, right? Because UN is not gauged.
Well,
what's the of
in that sense, UN is gauged. I mean, I am declaring that I only look at UN invariant observables. Now you can ask how I can impose that projection just onto the UN invariant observables. And well, if I want to do that in a local way, then the only way would be to gauge UN. So in some sense, this UN is gauged. I'm just not committing myself to exactly how I gauged it, because if I gauge it, I would also add more degrees of freedom coming from the gauge fields and so on. But I'm imagining that I can somehow project to these UN invariant observables without adding additional fields. That it's a somewhat subtle question how to do that, but at least in 3 dimensions, it's possible to do that by adding gauge fields with a Chern-Simons coupling and then taking that level to infinity. In higher dimensions, it's more subtle to do it, but again, the details of how exactly I do it will not play a role in this talk. So in this talk, I'm just imagining that I have some projection just to the UN invariant field, and then those are really the only observables of my theory. I just don't have any other observables.
Okay, that's fair enough. Okay.
So then in the first step of the derivation will be to change variables from the phi's to these bilocals G. Now in the next step, well, the next 2 steps will be trying to map these G's to fields living on anti-de Sitter space. And for that, I'll use an important property of this correspondence that I didn't describe so far. So it turns out that anti-de Sitter space in d+1 dimensions, its isometry symmetry is not the Poincaré group like we have in flat Minkowski space, but it's the group SOD plus 1, 1. It looks like the Lorentz group, but it acts as isometries on this on this Euclidean anti-de Sitter space in d+1 dimensions. And that symmetry maps on the quantum field theory side. This maps to the conformal symmetry of d-dimensional field theories. So in d-dimensional Euclidean field theories, if they're invariant under conformal transformations, then those form this group SOD plus 1, 1. And of course, a free massless scalar field has conformal symmetry. So that's one part of this huge symmetry group that I described before. And so I'm going to use the fact that we know how this symmetry acts on both sides of this correspondence. On the anti-de Sitter space, it just acts as these isometries, which are just rotations of anti-de Sitter space. And in the quantum field theory side, it acts as a conformal symmetry. And of course, the matching of these 2 things is a basic property of this correspondence. So in order to construct the mapping, it will be useful to take this bilocal field and to expand it in eigenfunctions of this SOD plus 1, 1 group. So in some sense, to just decompose it into representations of SOD plus 1, 1. And it turns out that if I do that decomposition, then, well, decomposition includes various representations of this d plus 1, 1. So I can construct functions h delta 1, h delta j of x1, x2, y. So these are functions labeled by parameters delta, which is some number, j, which is some integer number, and y, which is some point in space-time. And the claim is that there is a basis of functions of this type, which are eigenfunctions of this conformal symmetry, and which form a complete basis for all the possible functions of two variables. So I can take my functions gx1 of x2 and expand them in this basis with some coefficients c delta j of y. So this is one expansion that I can do. And again, the motivation for doing this expansion is that since I know how the SOD plus 1, 1 group acts on both sides, that will help me to map between the two sides. And then in the third step, what it will do is we'll take spin J fields that live on anti-de Sitter space. So in the coordinates that I used before, say, they can be labeled by a d-dimensional coordinate x and this radial coordinate z. And then it turns out that with a few extra assumptions that I'll describe if I have time later, that when I decompose these fields all again into eigenfunctions of this SOD plus 1 group, then it turns out that exactly the same representations appear when I decompose those functions into representations of SOD plus 1, 1. So we have now some different functions, but they're still labeled by the same delta j and y. So now these are some functions of x, z, and y. But the claim is that I can still construct eigenfunctions that sit in those specific representations of SOD plus 1, 1 labeled by delta j and y. I mean, the reasons for these labels are that if I think of this as the conformal group, then the natural representations of the conformal group correspond to primary operators with some dimension delta and some spin j that sit at some point y. So these objects sit in the same representation as these primary operators of the conformal group. And the claim is that when I do this decomposition, then exactly the same representations appear here in the decomposition of this spin j field, so that I can again expand this spin j field in exactly the same living in anti-de Sitter space in exactly the same representations. And then once I have these two decompositions, then I can easily perform the mapping between the two sides, essentially just by identifying these two coefficients. So that gives me just some explicit linear map between this bilocal field that I had in my field theory and these spin j fields living in anti-de Sitter space. And then using this map, I can take this quantum field theory path integral and just rewrite exactly the same path integral. After doing all these changes of variables, I can write it as a path integral over these spin j fields living in anti-de Sitter space with some action that I can explicitly compute, which comes, well, it's a contribution both from the original action and from the Jacobians of all these changes of variables, but we can explicitly compute all of these contributions. And we also know how to map G to the other side, so any observable that I want to compute, it will now become some observable that's expressed in terms of these quantum gravity fields. So by following through this chain of changes of variables, I'll be able to rewrite my quantum field theory path integral, which I can use to compute any observable that I want, in terms of this quantum gravity theory in anti-de Sitter space, where again, it's a quantum theory that I'm writing in this path integral formalism. It's just a path integral over all the fields of this gravitational theory with some specific action that we can compute and with some specific mapping of the observables. So since so are there any questions at this point before I go into a few more details? I don't have time for many details.
So one question,
Yes.
You're getting a local theory in the ADS space. You have to assume that n is very large to do this, and what will happen if n is not very large?
Yeah, so that will show up in a moment when I discuss the details of this step. So here the dependence on n will become clear. So that will become clear in a moment, I hope.
Okay, good. No more questions?
Okay, so I probably won't have time for the details of the second and third step, but these steps are rather technical. In some sense, the main step is this change of variables from phi I to this bilocal. So let me say a few more words about that change of variables here on this other blackboard. So one of the non-trivial steps in this mapping is to change variables in this path integral from the phi's to this bilocal. And the problem with doing that is that this is a nonlinear change of variables, and these g variables are not really independent of each other. So for instance, it's clear that if n is equal to 1, then if I had just one scalar field, then this G would just be phi dagger x1, phi of x2. So it would have a constraint that looks like gx1, x2 times gx3, x4 would be manifestly equal to gx1, x4, gx2, x3 for any 4 points in my spacetime. So obviously the G's are not independent. And for higher values of n, you can show that I don't have as simple constraints as this, but if I look at a product of n plus 1 G's or more, then at various points, then those obey rather complicated constraints that come from, again, from the fact that these G's are ultimately just built in terms of n fields. So this is what complicates this change of variables, the fact that these G variables are not independent of each other. So here is really, in some sense, where this large n limit comes in. So if I take the large n limit and I do an expansion in powers of 1 over n, so which is one of the things, well, again, we expect the gravitational theory to be a quantum theory where 1 over n is, in some sense, it's h bar parameter, so that controls the length of this of the quantum corrections. So it's natural to try to take this theory and do an expansion in 1 over n. So when I do that, so when I take n to infinity and expand in 1 over n, so in that context, these constraints are just invisible. So these constraints are, if you want, non-perturbative from that point of view, because this is like 1 over n, so it's 1 over the coupling constant here. So in this expansion, as long as I do this expansion, I can just ignore the constraints, and I can just perform this change of variables, compute the Jacobian for it. So again, in the large n limit, when I ignore the constraints, there is a well-defined Jacobian for this change of variables. And then I can just perform the change of variables, go on, and write down a theory using these G's, which I can then map to the quantum gravity fields. And that's what I'll do in a moment. However, if I'm not taking n to infinity, if n is some finite value, which is what I ultimately want, say, if I want to understand the non-perturbative mapping between the two sides, then I do have to take these constraints into account. So in order to describe the non-perturbative effects, well, one main effect that we'll find non-perturbatively is that products of n fields or more will obey various constraints. Now, in the field theory side, that's true for products of these bilocal operators, but by our mapping, these will become products of gravity fields. So these G's just map to linear combinations of the gravity fields that we have on the gravity side. So even though perturbatively we'll be able to construct a theory which on the gravity side will just look like a standard path integral over these gravity fields, the graviton and fields of any other spin here on this anti-de Sitter space, non-perturbatively we'll find that these fields obey various constraints, which will be highly non-local, such that in some sense these variables will turn out not to be very useful non-perturbatively, because we don't know how to solve these constraints for finite n. So if you want, the punchline of the talk is going to be that we can, when we use this type of mapping to derive the Ads Cfd correspondence, then we do find indeed that at all orders in the coupling constant, we do find a theory that looks like a perturbative quantum theory of gravity and all these other fields living in anti-de Sitter space. So you might have thought that you can really write the theory as some path integral over gravity and summing over metrics and topologies and so on. But in fact, what will turn out is that non-perturbatively, this graviton is not really a good variable because it obeys complicated constraints that are not visible at any order in perturbation theory, but which are a manifest property of this mapping. And again, we can write them down explicitly if we want. They're just relatively complicated. So I think since I'm almost out of time, then this is the main point that I wanted to make, that we have these constraints. Now, if I ignore these constraints for now, then ignoring these constraints, then this mapping is just invertible as long as I ignore the constraints. So I can just do this this change of variables in the path integral and rewrite this as a path integral over this G with some Jacobian that I can write down as some determinant of this G raised to some power, and then compute manifest the action for this G. And then again, I have these other two technical steps that are just these decompositions. So let me just say a few more words about them just to make them well defined. So this decomposition on the field theory side is completely well defined. I mean, we know how the conformal transformation acts on these G's, so we just have to take this product of two phis and reduce and expand that into irreducible representations of the conformal group. Now on the quantum gravity side, then things are more subtle because it's not even clear what I mean by fields living on anti-de Sitter space. as I told you, when we have a quantum gravity theory on anti-de Sitter space, then the metric fluctuates, and we don't even have a fixed space-time. So what do I even mean by these fields on anti-de Sitter space? So the point is that in these high-spin gravity theories in anti-de Sitter space, I have such a huge gauge symmetry. So I have in particular the symmetry of diffeomorphisms associated with the massless spin 2 particles, but I also have a much bigger symmetry associated with all the massless spin j particles. And it seems that that symmetry is enough so that it allows me to always fix the metric on my spacetime, in some sense, to be the metric of ADS space, and then to just expand all the other fields as fluctuations around that metric. So there is a formulation of that high-spin gravity which writes all the fields as just fluctuations around a specific metric. So if you want that sort of a highly gauge-fixed formalism of this high-spin gravity theory, where I gauge-fixed the diffeomorphisms and also all the other high-spin symmetries in order to be able to write the theory in terms of fields living on a fixed anti-de Sitter spacetime. But once I do that and I write the fields living on a fixed anti-de Sitter spacetime, then I can perform this expansion of those fields into irreducible representations, and then I can do this mapping. So I mean, so this comment was important to avoid confusions. As I said, in theories of gravity, we don't have any local observables. Well, this phi j, it does look like it's a local observable that's sitting here at some point in the bulk, and which is well defined because it's just some linear combination of these observables that I had in my quantum field theory, which were well defined. So the reason that I can have such well-defined observables is that essentially I gauge-fixed all of the diffeomorphism symmetries and all the other high-spin symmetries, and that gauge-fixed formalism, I do have these local operators in the anti-de Sitter space. Unfortunately, the action for these operators will still turn out to be highly non-local. So since I'm almost out of time, then let me just exhibit a few formulas to sort of illustrate some aspects of this mapping. I mean, people who are interested in more details can find them in our paper. So this is the explicit form of the mapping from this bilocal operator. So this Erez is some rescaled version of this bilocal G. And this is an explicit formula for how we map it to these spin J fields in anti-de Sitter space. So all of these functions and symbols appearing here are just known functions that can be written down explicitly. So it's a complicated mapping, but it's completely explicit. So given any configuration of the bilocal field, I can map it to a configuration of the fields living in anti-de Sitter space, and it's an invertible mapping so that any function of these fields in anti-de Sitter space I can translate into a function of the bilocal fields. And then again, using that, I can just take my action that I wrote down for the phis together with this Jacobians and translate that into an action of the fields living in anti-de Sitter space. So an example for one of the terms in the action that I get would be this. So this is the third order term in the fields that I get in my action in anti-de Sitter space. So as expected, it goes like some negative power of n, so it's showing that this theory becomes weakly coupled for large n. And so as you see, it gives it a somewhat complicated interaction between these three fields of different spins that live at different points in this anti-de Sitter space. Now these interactions are highly non-local. I mean, my mapping did not conserve any locality properties, so these interactions are highly non-local. But that's to be expected just in this case where I have a weakly coupled field theory on general grounds, as I described before. And even though they're non-local, they are completely explicit, so that we can just take this action and use it for computations. I mean, we're not used to computing with non-local actions, but in principle, we could just use the same rules as we use for local actions. And by construction, this action with these interactions of the gravity theory on anti-de Sitter space will give us exactly the same theory as the quantum theory that we started from. So in that sense, what we have is a derivation of the Radius Cft Correspondence, where we rewrote our quantum field theory in terms of these new variables that are these fields in anti-de Sitter space. So again, order by order in 1 over n, the form of our mapping guarantees that this quantum field theory of these gravity fields in anti-de Sitter space, which is non-local, will reproduce for us exactly the same results as we had in the field theory. And then if I want to do it for finite n, as I said, we have to add in also these extra constraints. So just one final comment before I summarize. You may be worried about the fact that I have here just a free field theory, and you may wonder that maybe free field theories are not so interesting. But once I understand this mapping for a free field theory, then I can just take that as a starting point to describe also interacting theories. So for instance, I could add here to the action also some interaction term, like I could add minus lambda over 4th phi I squared squared. So if I do a fourth interaction and so on, so once I have this full path integral mapping, I can easily also add interactions on the field theory side and also map those into some specific change in action on the gravity side. So this, so even though I described the free field case because that's the simplest one, then this type of mapping is definitely not limited just to free fields, but it can be generalized also to interacting fields. So since I'm out of time, then let me just summarize. So to summarize, I constructed explicitly a specific example of the Ads Cfd correspondence where I constructed a quantum gravity theory, which by construction is completely equivalent to a theory of free fields living in one dimension less. Again, the result is non-local, but it is but it has a completely explicit action, which we can use to perform computations, which again, by construction, reproduce the answers of the free field theory to all orders in 1 over n. And I think it also illustrates an important principle of quantum gravity in general, that even though we do see the gravity variables as useful variables perturbatively in this 1 over n expansion, non-perturbatively, it seems that these gravity variables obey very complicated constraints, which we can explicitly describe. So it seems that theories of quantum gravity, so even though, so this is the form of the path integral perturbatively, but non-perturbatively, the path integral is much more complicated, and it's probably not very useful to think of it as the sum over metrics and topologies in the way that we would usually, or in the way that we would naively think of a theory of quantum gravity. So this is a summary of what we did. Now there are many future directions here. I mean, so as I said, our mapping gives us this explicit non-local action for these fields in anti-de Sitter space. Now we haven't shown yet that the equations of motion coming from this action in the classical limit are the same as the ones of Vasilyev's high-spin gravity theory. I mean, in some sense, that's probably guaranteed if high-spin gravities are unique, but it would be nice to show that explicitly. So that's one thing that still remains to be done here. Another thing to be done is the formalism that I described it. We really only look at the physical observables. So we're working in this completely gauge-fixed version of the high-spin gravity theory, where all the diffeomorphisms and all the other symmetries have been completely fixed. So in that sense, I mean, it doesn't really look like a theory of quantum gravity, which we would like to have, that has diffeomorphisms and all these other symmetries, because we just construct a gauge-fixed version of that. So it would be very nice to somehow undo this gauge fixing and write our theory in a way that does explicitly exhibit the diffeomorphisms and all the other groups. Again, we do know that we have a theory of quantum gravity because we have a massless graviton in a quantum theory. So on general grounds, we expect it to be a theory of quantum gravity, but it would be nice to write the theory in a way that explicitly exhibits also all the gauge symmetries that we expect a gravitational symmetry to have. There are many generalizations of this analysis that we're studying. One can, of course, generalize from scalar fields to fermion fields. One can discuss the theory on other manifolds. There we go back to Shinji's question. As I mentioned in answer to Shinji's question, if we work just in Euclidean RD, then it's easy to just project onto Uninvariant variables, and I don't have to say specifically how I say that. But if I would look at other manifolds, and even say just RD minus 1 cross S1, then here, or if I want to project onto Uninvariant variables, I do have to also add Uninvariant gauge fields, or at least some holonomy around this circle. So the theory becomes much more complicated, and we don't know yet how to do that. So for now, our mapping is limited just to flat Euclidean space. It would obviously be interesting also to generalize this to the Lorentzian case. So, I mean, in principle, the same type of consideration should work also in the Lorentzian case, but the form of the conformal group is somewhat different there, so we haven't studied yet exactly what this looks like. Another interesting generalization would be instead of anti-de Sitter space to de Sitter space, which is the maximally symmetric space of positive cosmology, which arises as a solution of Einstein gravity with a positive cosmological constant, like we have in our universe. So there is also a version of this Radius Cft Correspondence that works for de Sitter space, and it would be interesting to try to generalize this approach to that case. And of course, what we'd like most to do is to go away from this, from these very esoteric high-spin gravity theories in the direction of gravitational theories that are more similar to Einstein gravity, where we do have an approximately local theory with a large range of scales between the Planck scale and the curvature scales. So that is the ultimate goal of this program, but for now we're just doing the first steps, and well, this is what we have so far. So thank you very much.
Thank you very much, Ofer, for a fantastic talk. That was really enjoyable to see a Blackboard talk again. Questions that I'm going to go straight into. First question is, what is your motivation for choosing anti-de Sitter metric, knowing that we have many other metrics?
Yeah, so that's a very good question. So of course people have studied quantum gravity also in other spaces. I mean, an advantage of choosing a maximally symmetric space is that you have more symmetries. I mean, so it's easier to work the more symmetries you have. So in some sense, the spaces that have the maximal symmetry are either just flat Minkowski space, or de Sitter space, or anti-de Sitter space. Those are the spaces that have the largest isometry groups, so that they're the simplest to study. And then, well, people have tried very hard to study quantum gravity also in these other cases, but so far, unfortunately, not much progress has been made in those cases. While in the case of anti-de Sitter space, we have been able to make much more progress because of this miraculous equivalence between quantum gravity theories in this space and standard quantum field theories. So again, of course, we're not interested in this space specifically. We'd like to understand quantum gravity on any possible space. But for now, this is just all that we know how to do. Again, thanks to this miracle of the Radius Cft Correspondence.
So the next question is, while the gravitational action is explicitly non-local as written, effectively local on scales larger than L?
Right, so that's an excellent question. So indeed, from the way that I wrote it, it's not even obvious that it's local at distance scales that are bigger than the curvature scale. And yeah, that's something that we'd like to understand better. I mean, we do expect it to be, I mean, since in some sense the non-locality scale should be the same as the curvature scale, but not larger, then we do expect this to give a local theory at larger length scales. I mean, we have some indirect evidence for that, but indeed it's not evident from the way that I wrote the action, and it would be nice to understand that point better. So yeah, that's an excellent question.
Okay, so the next question is, can you comment on what elements of your analysis would still be applicable if you were to consider something like a non-abelian gauge theory?
Yeah. Okay. So the main thing that helped us in the analysis here was the fact that this is what's often called a vector model, where there's really just a very small number of observables that are invariant under the UN group. Namely, it's only these bilocals. If I would have a non-abelian gauge theory, where I'd have some non-abelian gauge field. So in a non-abelian theory, I would have some non-abelian gauge field, say F nu A at X. And in a theory like that, I can write down many observables that are invariant under the UN group. For instance, I could write down the trace of any, let's say, U1 at point x1 with an x a1 and so on. And so a trace of any number of these fields would give me an independent, in the larger limit, an independent UN invariant observables. So just the number of UN invariant observables in a theory where I have these sort of matrices and the adjoint representation of UN is much larger than the number of UN invariant observables in the theory that we had, and the constraints between them are also much more complicated, unfortunately. So what will remain true is that if I go to the n goes to infinity limit, then it is true that the constraints between these variables will go away. So say if I had one matrix, then I would have all these trace x to the n variables, and these do become all independent in the limit that these are n by n matrices and n goes to infinity. These do become independent observables, and so the constraints would go away. But just the Jacobian for the change of variables from my original fields to this other basis of UN invariant observables just seems to be too complicated, so that we don't know how to explicitly perform this, even this first step of just the change of variables from the original fields to the UN invariant field. So that may be a technical question, but I suspect that it's more than a technical question. I mean, I suspect that for these more complicated cases, it won't be really enough to write down something that looks like a local theory, even though, well, the interactions are non-local, but I still write it using local fields. I suspect that once we go to gauge theories, to non-abelian gauge theories, it will be important that it's actually a string theory that has also non-local objects like strings and branes and so on, and those will also have to come into the game somehow, but well, we don't know how to do it. I mean, so again, at the technical level, we just get stuck that we don't know how to do this change of variables, and I suspect that it's not just a technical point, but that it's really a conceptual point that quantum gravity theories that are dual to non-abelian gauge theories are just more complicated than this. Even in the classical limit, they should become classical string theories and not just classical theories of some relatively small number of fields. and then different tools are probably needed to study them.
Okay, Ofer, thank you very much for the excellent talk. I think Robert indicated that there are no further questions, and I know that all good talks are good until they don't exceed an hour too much. So thank you very much for sticking to the time. And yeah, it's just my job now to thank you very much for your time and for sharing this great overview of the road towards quantum gravity. And I'm sure that we will need to invite you again in a short while to share with us how the story evolves. So thank you very much also, of course, to Robert for moderating the questions and for facilitating the talk by Ofer. And a big thank you to all the participants for being with us every Monday afternoon. And I hope that the announcement of the next talk should be in your inbox very soon, so that we will see you again in a week's time. So thank you very much, everyone. Thank you very much, Ofer, for your time. And we'll see you again next week. Thank you. Bye-bye.
Thank you very much, and goodbye.
Thank you, Ofer. Thank you very much.